So good morning, students. Today we
Good
would be
morning, ma'am.
morning. Today we would discussing about this topic about the difficulty in training deep neural network, followed by other topics, which is gradient, greedy retraining. In this file, I'll be sharing in the classroom. What happens in this is that when you are training a deep neural network, if you recall, deep network has got multiple layers, many layers. Training a shallow neural networks is different from training a deep neural network. In a shallow neural networks, you might have neurons in layer 1, layer 2, layer 3, and maximum up to layer 10. Whereas as you increase the number of layers up to 50 layers or 100 layers, then the techniques that were developed for training shallow neural networks will not work properly, such as the activation functions. Essentially, training a deep neural network um, presents lot of challenges. It's not as simple as training a shallow neural network. If you recall, when an input is feeded to the first hidden layer, consider that this is the first hidden layer. In this layer, two operations we are performing: summation operation and then activation. When you perform the sum of input into weights and you pass this to the activation function as input, then this activation function um, applies a specific formula, whatever is the activation function you have employed. If you consider a sigmoid activation function, the sigmoid activation function has an equation of 1 over 1 plus e to the power of minus x. In this, the output ranges between 0 and 1. And um, as you go along these hidden layers and compute the activations, and you generate output from this neural network. This output you compare with the actual output, and then error is propagated back. When you are propagating the error back, what happens is the weights are updated. You are updating the weights, and followed by you are using the gradients of this activation function. uh, when you use the gradient of sigmoid activation function and you go on back propagating the values, uh, the gradients gets reduced at every stage, and finally you will not have any gradient. It will be close to zero. When it is close to zero, that value will not have any effect further when you are going in the forward direction. This condition is known as vanishing gradient problem. And a similar situation arises when the gradient value reaches to a value closer to 1. When you have a gradient value closer to 0, it is known as vanishing gradient. When you have a gradient value closer to 1, it is known as exploding gradient. Even when the gradient explodes in the sense is closer to a value 1, you don't get any variation, and output closer to the actual output in these two conditions, when there is a vanishing gradient and exploding gradient. Therefore, this gradient problem, when gradient is uh, becoming closer to 0 or closer to 1, is known as gradient saturation. When gradients get saturated, whenever gradient gets saturated, uh, there won't be any impact of that value on the output. However, we would like to have a value which is um, closer and closer to the actual output. To obtain that sort of value from the neural networks, our gradients play a major role. That weight updates through through gradients you are updating the weights, and this weight updation will influence the output of the neural network. So essentially, here the difficulty in training neural network lies with sigmoid gradient, this sigmoid activation function. These are the papers. You have to study the papers, research papers that will perform some experiments and state their results and discuss their results and come to a conclusion saying that this is better or that is not better. These papers which have been given in this document, you please go through these papers. These papers says that this effect of activation functions and saturation during training when we are using the sigmoid. It is stated that the gradients will not propagate well, and overly linear units. When you have a linear unit is producing the output which will only have um, linear function as the prediction. It does not properly model the non-linear function. So when you have this sigmoid saturation, when sigmoid does not play a vital role in this computations, then the output is closer and closer to the linear output. So when it is linear, then it will not have uh, linear means, if you recall, linear is just a straight line that segregates two classes, nothing else. On the contrary, nonlinear function models several different kinds of functions, like in this manner, circle, or in a more complex manner, different shapes it can produce. This is non-linear. Linear means just a straight line. All right. Um, the similar problem exists in hyperbolic tangent. The difference between a sigmoid and hyperbolic tangent is, sigmoid is a S-shaped function that generates output between 0 and 1, and hyperbolic tangent or tan H function is also a sort of S-shaped function. Oh, however, its output values ranges between -1 to +1. So you have like this, um 0, -1, +1. So this tangent values will have a range like this, +1 to -1. And sigmoid will have +1 and 0 in this manner. It won't go down this line. Uh, Apparently, tonnage exhibits the similar kind of problem of gradient saturation. When gradients saturate, it will not have any impact, as I told you, and output will not give variation. There is another activation function known as soft sign. Even this one does not produce a value which will have much difference. Even that gives weight saturation, gradient saturation. Yes. Is that topic clear? What is happening when you are applying back propagation? Weights are updated. You recall we have this weight of new is equals to weight of old minus this eta learning rate, and then here you have this uh, cost function, which is nothing but derivatives of loss with respect to the weights. In this manner, you are back propagating the error, and through the gradients of the function, new weights are computed by using optimization functions, optimization algorithms like uh, gradient descent, stochastic gradient descent, uh, batch gradient descent, Adam, momentum, RMS prop. These are different optimization methods. So the bottom line here is that gradients should not get saturated, and there should be no vanishing gradient and exploding gradient problem in the model. And because deep neural networks involves multiple layers, this problem is prevalent in that. Therefore, a new method was devised that we will look at when we study optimization methods. Here, studying gradients and their propagation. What is the effect of cost function? The output that is generated, say the model generates output 8 and the actual output is 10, and when you say 10 minus 8 you get 2, and this 2 is the loss. This 2 is the loss. And how are you getting this 2? By means of cost function. What is the effect of cost function? Okay. uh, to come to that point, here what this paragraph state is that gradients weights have to be initialized. When you initialize the weights, you can do the weight initialization normally. Normally means you just leave that weight initializations to the model. Randomly it initializes, or you can use some kind of mechanism in order to initialize that. And you can initialize by using different mechanisms, so that it gives different error values based on that weight initialization, and also using this activation function and various weight initialization. What happens is different loss values will be generated. Okay, you get different loss values, and in order to have a lower loss, we can go for different mechanisms to initialize the gradients. This is one of them. So you can use these weights, which is approximately equal to this value, which if you put on the values, you get some number. That number you initialize to the weight. This is known as normalized initialization, because you are dividing uh, this root 6 with the weight, with the values, that is total number of here n of j denotes the total number of um, that elements, that nodes, total number of nodes. You, when you divide this total number of 6, you can take any value. For instance, here if it is taken 6 over total number of nodes will give some value that you initialize to weights, which is known as normalized initialization. This normalized initialization, when you plot, will give different activation values at different layers. You see layer 1, 2, 3, 4, 5, and then here different initialization will give different activation values for different this layers. Here you see this is different, and this one all are uh, de- you know presented in the form of a normal curve. So here, this weight initialization by using different values will have a different effect on the loss value. And then there is another topic known as greedy layer-wise training. We have studied that training deep neural network presents a challenge of vanishing gradients, which means that weights in the layers gets closer and closer to zero, and therefore they don't get updated. And because they are not updated, there won't be any much impact on the output or the prediction of the model. uh, there is this topic known as greedy layer-wise training. This is an innovative and important method that allowed this very deep neural networks to be successfully trained by using state-of-the-art performance. And in this, what we learn is how to perform greedy layer-wise pre-training. And what does this uh, produces? What is the effect of this? So, a greedy layer-wise pre-training, this provides a way to develop a deep multi-layered neural network, whilst only ever training shallow networks. When you're training a shallow network, that is quite different from training a very deep neural network. And pre-training can be used to iteratively deepen a supervised model or an unsupervised model that can be repurposed as a supervised model. You can modify a unsupervised model in the form of a supervised model, and also you can train a deep supervised model iteratively through pre-training. And this pre-training is useful for problems with a small amount of labeled data and a large amount of unlabeled data. So what happens in this pre-training is, so pre-training involves successively adding a new hidden layer to a model and refitting, allowing the newly added model to learn the inputs from the existing hidden layer, while keeping the weights of the existing hidden layer fixed. And this technique is known as layer-wise uh, training. And this technique is referred to as greedy because uh, the training is happening in piecewise or layer-wise approach, not training the entire model at once. Your training, if you have consider that you have 20 layers like this, one and so on up to n, and no, up to 50. When there are 50 layers, you don't send the input through all these hidden layers to generate the output from the output layer. Instead, you train first few network layers, say layer 1, 2, you have trained, and then you get some loss. And then what do? You train another set of hidden layers. Mama, you add more hidden layers and then you train. And further you add more hidden layers and then you train. Like this, you have split up training of the model into piecewise training or layer-wise training. It's not like feeding the input to input layer all the way from hidden layer 1 to hidden layer 50 in a forward direction, getting the output and then comparing the output with the actual output and back propagating through 50th layer to 49th layer and up to the first layer, updating the weights. During this process, what problem might occur? Vanishing gradient problem might occur. What is vanishing gradient? By the time this back propagation reaches layer 1 or 2 or 3, gradients might have become 0. When gradients are 0, then it won't give much change in the weights. Um, so apparently, uh, this method was devised, which is known as layer-wise training. It is greedy because you are doing it in layer-wise manner, not in the complete uh, network. You are not doing it in a complete network level. You are doing it in layer level. At each layer, or you can combine it into 2, 3, 4 layer. This is nothing but pre-training. This is known as pre-training. What are the benefits of pre-training? The training process would be simplified. Why it would be simplified? You train a model and then you have got the model which is generating some kind of output. To that you add some more layer and you check whether it is improving or not, and then you to that you can add another layer. You are not doing at once for all the layers, so it is very much simplified and it facilitates development of deeper networks. In this manner you can proceed into any number of layers, and essentially this training of deeper and deeper networks is simplified and uh, gets easy, and it is also useful for weight initialization scheme. Weight initialization process uh, would be uh, how it would be is for this network you have initialized some set of weights, and these weights you can use as it is when you are adding some more layers. Again, it depends, it depends on how you are approaching this problem. You can reuse the weights that have already been trained, or you can train once again. And when you are using already trained weights you are using, and then you know that this initialization works well in this segment, then you can perhaps use the same initialization scheme in this segment as well. And perhaps lower generalization error. Generalization error is the one that that is not specific to a particular set of data. Generalization really helps when you have a variety of data. You are working on one fragment of data, and then you use another fragment for testing, which does not include much of the features of this training. All right. Then what happens when you have this kind of data? You should generalize your model. Model should be able to learn so effectively that it should be able to identify different kinds of data. Okay, so it can lower the generalization error. And there are two main approaches to pre-training, that is supervised layer-wise pre-training, unsupervised layer-wise pre-training. Supervised, can you tell me what is supervised and what is unsupervised? In supervised training, we know that the data set has uh, the features and the output value. The features and the output value in supervised training. In unsupervised training, you have only the features. There is no y, there is no output value. So what you have to do is you have to group them into some kind of clusters. Okay, that is unsupervised. So you can use pre-training for both supervised and unsupervised uh, models. This multi-class classification problem. What do you mean by multi-class classification? When you have binary class classification problem, this binary class classification will have only two classes. For instance, if you have a data set of cats and dogs, okay, this is known as two class classification. There are two classes. And when you have a multi-class classification, it can be 3 class, 4 class, 5 class. If you have, say, cats, dogs, horses, zebras, these are four class classification problem. So how this multi-class classification problem uh, is implemented by the use of pre-training, and what is the effect of performance effect on performance, model performance, that we will look under this one. All right, this scikit-learn library, this is a Python library. This has got API for various machine learning problems, and for data set splitting, for model performance, for these different tasks. Scikit-learn library provides API. So here, uh, make blobs is a function of scikit-learn that can be used to create multi-class classification problem with the prescribed number of samples, input classes, and variance of sample within a class. This is, here we are using make blobs function, where we have 1,000 samples, and there are 3 centers, and there are two uh, features, and standard uh, cluster standard is 2 and random state 2. These are the parameters which you are passing to this make blobs. what it does, it generates uh, the data set x and y, and then this can be plotted by using scatter plot. You are using this sklearn dot dataset import make block. Sklearn is nothing but scikit-learn, and this matplotlib is also a library from which you are importing pyplot. It is a function to plot the elements, the data elements. And NumPy is a numerical Python library for scientific computation of numbers. And then here you are generating x and y, and you are plotting the values using this scatter plot. And this uh, standard deviation which you have specified cluster std, uh, that denotes that the data, the classes are not linearly separable. Linearly separable, again I am telling you, which can be separated by a straight line. When it is not linearly separable, then it requires non-linear function. And look at this. This is the data set plot. We have three classes. One class is denoted by blue, another green, and another, the last one, orange. Can you separate this by drawing a single line? If you draw a line like this, then you are separating only these two classes. Which two classes? Blue, and the other one includes further two classes, which is not right. Okay, so here we have to somehow create this non-linear structure. This is not a line, this is sort of triangle which will separate. No, it should be from here, should be this, like this. So this part, this region has all orange colored classes. And you look at here, some of the green samples also have gone into this section. So the model should be able to clearly distinguish this blue, green, and orange. So like this and like this, perhaps can perhaps can segregate these multi-class classification. Okay, so supervised grady layer wise pre-training. Supervised, we know that in supervised training we have the output, and then the program is given how you can execute this. We will execute and see, like this kind of output you get. uh, that's really practical, that has the programs. For these two programs we will execute and see how this works out in tomorrow's class. And any doubts in today's class? If no doubts, we will wind up today's class. We will meet tomorrow. Okay, bye.